Close your eyes for a moment. Imagine standing at the edge of the coldest place on Earth. The wind isn't blowing, it's screaming. Temperatures that would freeze exposed skin in under 2 minutes. A landscape so hostile, so unrelenting, that the very air itself feels like it's trying to erase you from existence. Snow in every direction, ice in every direction, nothing else. You've been told this place is empty. You've been told this place is dead. Scientists told you, textbooks told you, the entire scientific consensus of the 20th century told you, Antarctica is a barren, frozen desert, a continent of beautiful desolation where almost nothing lives, almost nothing moves, and almost nothing changes. They were wrong. Between November 2019 and January 2020, a team of Italian researchers trekked across one of the most remote corners of northern Victoria Land, a region so isolated, so brutally cold, that even seasoned Antarctic explorers rarely venture there. Average temperatures hover around -41 degrees Fahrenheit. The wind doesn't merely blow, it sculpts, it carves, it erases. And this team was looking for a lake. Not just any lake, a place called Enigma Lake, a name so perfectly chosen it borders on prophecy. On the surface, Enigma Lake didn't look like much. From a satellite image, from a weather map, from any rational scientific framework, Enigma Lake should not have existed at all. Antarctica is technically classified as the world's largest desert, not because of heat, but because of an almost total absence of precipitation. Rain is essentially unheard of. Snowfall is surprisingly minimal, and whatever moisture does reach the surface is obliterated almost immediately by katabatic winds that race down from the polar plateau at speeds that make hurricane-force gusts seem gentle. Any liquid water should have evaporated, should have frozen solid, should have been consumed by the relentless dryness of the continent ages ago. The lake was losing, by conservative scientific estimates, roughly 7 million cubic feet of water every single year, just to wind and evaporation. And yet, the water remained. The team deployed something called ground-penetrating radar across the surface of Enigma. Think of it as a kind of echolocation for the Earth itself. The same principle dolphins use to navigate dark water. The same principle bats use to hunt in absolute darkness. The radar sends invisible waves down through the ice. Those waves hit something, a rock, a void, water, and bounce back. By measuring how long the signal takes to return and how strongly it echoes, you can map what lies beneath the surface without ever drilling a single hole. The readings came back, and what the radar found beneath at least 36 feet of permanent ice, beneath a frozen ceiling higher than a 3-story building, was liquid water. Not ancient ice, not compressed glacial material. Liquid water. And inside that water, in that cold, lightless, utterly isolated pocket of impossible existence, something was alive. This is the story of a continent that has been lying to us, not through deception, but through scale, through a vastness and a silence so enormous that we simply lacked the tools, the technology, and perhaps the imagination to understand what was truly there. Antarctica is not a graveyard. It is a library, and we are only just learning to read. Let's slow down here for a moment, because the existence of liquid water at Enigma Lake isn't just surprising. It isn't just interesting. It is, from a purely physical standpoint, essentially impossible. And the fact that it exists anyway tells us something profound and unsettling about how little we truly understand about this continent. Walk through the math with us. Antarctica receives less precipitation per year than the Sahara Desert. The winds that scour the northern Victoria land region, where Enigma sits, can exceed 120 miles per hour. Those winds are not merely cold, they are desiccating. They strip moisture from every surface they touch with an efficiency that rivals the driest environments on the planet. Scientists calculated that Enigma Lake should be losing approximately 7 million cubic feet of water annually to this combination of evaporation, wind erosion, and sublimation, the process by which ice converts directly to vapor without even pausing in a liquid state. 7 million cubic feet. Every year. Gone. And yet the lake, which the ground-penetrating radar confirmed holds at least 40 feet of liquid water beneath its permanent ice cap, was still there, still full, still somehow being replenished. The Italian research team stared at this paradox the way you'd stare at a magic trick you cannot explain, even after you've seen it performed a dozen times. There had to be a source. There had to be something feeding the lake from below, from beneath, from somewhere no one had thought to look. They analyzed the chemical composition of the water, the salt concentrations, the dissolved minerals, the ratios of isotopes, different versions of the same atomic elements that act like fingerprints, telling scientists where water came from and how long it has been traveling. The readings pointed in one direction, the nearby glacier. There was, and this is the part that should stop you cold, an underground pathway, a subterranean network that nobody had expected to exist, threading through the rock beneath the glacier, channeling glacial meltwater down into the basin where Enigma Lake sat. Not a river, not a stream. Something older and stranger than that. A hidden plumbing system built over thousands of years by the slow, patient movement of ice and the equally slow, equally patient dissolution of stone. And this matters far beyond the immediate story of one strange lake in one remote corner of Antarctica. Because in the early 2000s, scientists studying the Gamburtsev mountain range, a massive mountain system buried under more than a mile of East Antarctic ice, completely invisible from the surface, began piecing together evidence for something extraordinary. Using seismological instruments and, later, a technique called ice-penetrating radar, they discovered that beneath Antarctica's fastest-flowing ice streams, there wasn't simply solid rock. There was a network, a web of subglacial lakes, rivers, and channels stretching across hundreds of miles, an entire hidden hydrological system operating in total darkness at temperatures just barely above freezing, under pressures that would be lethal to most surface life. Hundreds of lakes. Connected, flowing into one another, draining into the ocean, and then refilling through processes that scientists are still working to fully understand. In 2007, a satellite called ICESAT, NASA's Ice, Cloud, and Land Elevation Satellite, began capturing data that confirmed something astonishing. The ice above these subglacial lakes wasn't static. It was rising and falling, slowly, almost imperceptibly, but measurably. The lakes below were filling and draining in cycles, pushing the ice sheet up as they filled and allowing it to sink as they emptied. This was ice breathing. This was a continent, a place we had categorized as geologically inert, biologically barren, actively, dynamically doing something. Moving water, cycling nutrients, behaving less like a dead landscape and more like a living system. In 2013, a team from Scripps Institution of Oceanography, led by glaciologist Helen Amanda Fricker, published findings that would reshape the field. They showed that when one of these subglacial lakes drained, a process that could take days or weeks, it could release staggering volumes of water into the ocean. One drainage event they documented flushed nearly 200 billion gallons of fresh water into the Southern Ocean in approximately 3 days. 200 billion gallons in 3 days. To put that in perspective, that's roughly the volume of water that flows through the Colorado River over an entire year, delivered to the ocean in the time it takes most of us to get through a long weekend. And every time this happened, every time a lake drained or refilled, the ice above shifted, sometimes cracking, sometimes fracturing, creating pathways for new water to enter, creating conditions for new life or very, very old life to survive. The subglacial lake network beneath Antarctica isn't a geological curiosity. It's an active, dynamic system that may be one of the keys to understanding how our planet's climate has changed over millions of years, and how it will change in the decades ahead. But first, we need to look at what the Gamburtsev Mountains can tell us about an even older story. These peaks, buried under a mile of ice, stretching across an area roughly the size of the European Alps, formed during the creation of the supercontinent Gondwana, approximately 650 million years ago. Two massive sections of primordial Earth collided. The crust buckled and heaved. Mountains grew to Himalayan heights. And then, over the following hundreds of millions of years, as Gondwana broke apart and Antarctica drifted to the South Pole and gradually froze, those mountains were sealed away. They haven't experienced erosion in potentially hundreds of millions of years. The ice preserved them, the way ice preserves everything it touches, if the conditions are right. If the conditions are right, what the ice preserves can be more than mountains. It can be the atmosphere itself. There is a specific kind of silence at the bottom of a subglacial lake, not the silence of an empty room, not the silence of a quiet night. The silence at the bottom of Enigma Lake, beneath 36 feet of permanent ice, in water that has been completely isolated from the surface world for potentially hundreds of thousands of years, is the silence of absolute separation. A silence that has never been broken by a human voice, never been disturbed by sunlight, never been touched by wind or rain, or the slow drift of seasons. Into that silence, something alive has been building. The microbial communities discovered in Enigma Lake are not simple. They are not primitive in any casual sense of the word. They have spent an almost incomprehensible stretch of geological time, potentially millions of years, evolving in complete isolation, developing metabolic strategies, survival mechanisms, and ecological relationships that have no equivalent anywhere else on Earth. When scientists analyzed water samples from beneath the ice cap, they found 4 primary groups of microorganisms living in the lake. The first were bacteroidetes, bacteria that specialize in breaking down complex organic molecules. These are organisms we know relatively well. They live in our digestive systems, helping us process plant-based foods, and they're found in soils and ocean sediments worldwide. But the bacteroidetes in Enigma Lake weren't behaving quite like any version scientists had encountered before. They were adapting to a chemical environment, a specific soup of minerals, salts, and dissolved gases that exists nowhere else on Earth. The second group was Actinobacteriota, a phylum of bacteria that scientists sometimes call the engineers of the microbial world. These organisms are extraordinary decomposers, breaking down dead organic material and returning its nutrients to the ecosystem. They are also, incidentally, responsible for producing many of the antibiotics that modern medicine depends on. Streptomycin, erythromycin, tetracycline, all derived from Actinobacteriota. The third group was Pseudomonodota, perhaps the most adaptable bacteria on the planet. Pseudomonodota can survive in almost any environment: soil, water, extreme heat, extreme cold, the interior of the human body. Some members of this group are harmless, some are pathogenic. But in Enigma Lake, they had found their most extreme home yet. And then there was the fourth group, Ptacibacteria. These are not the kind of bacteria that show up in biology textbooks. Ptacibacteria are, by any measure, strange. They are ultra-small. Even by microbial standards, they are tiny, possessing stripped-down genomes that barely contain enough genetic information to sustain basic biological processes. They cannot produce their own energy. They cannot synthesize many of the molecules they need for survival. They are, in a very real sense, biological parasites. Organisms that depend entirely on their neighbors for the metabolic support they cannot provide for themselves. And yet, here they were, in Enigma Lake. In a place where the food web was presumably razor-thin, where every calorie of energy was precious, where survival meant finding some kind of niche so specific that no other organism had yet exploited it. Here were organisms that couldn't even feed themselves independently, somehow thriving. How? The current theory involves something called syntrophy, a kind of metabolic partnership so intimate that the organisms involved cannot survive without each other. The Ptacibacteria attach themselves to, or live inside, their hosts, sharing electrons, sharing metabolic byproducts, participating in a chemical conversation so constant and so complex that it begins to blur the line between two separate organisms and a single biological system. These organisms are hunters, not in the way a lion hunts, not in the way a spider hunts. They hunt at the molecular level, attaching themselves to neighbors and extracting what they need with a precision that makes them some of the most specialized organisms ever discovered. They could be ancient. They could be remnants of microbial communities that inhabited Enigma Lake before the ice sealed it off from the surface world, potentially hundreds of thousands of years ago. Locked in the dark, evolving, waiting. But Enigma Lake is not the only place where Antarctic life has defied every expectation science had set for it. The microbial mats, those complex carpet-like formations that scientists found covering the lake bed, deserve a moment of attention all their own. These aren't simple algal smears. These are structured, layered communities that build on themselves over time, creating formations that can resemble thin, spiky coverings in some areas, thick, crumpled carpets in others, And, most astonishingly, tree-like structures that can reach 15 inches in height. 15 inches. In a lake beneath 36 feet of ice, in a place with almost no incoming energy, where growth rates are presumably measured in decades rather than months. Tree-like structures in a frozen subglacial lake built by organisms that have never seen sunlight. In January 2025, an iceberg the size of the city of Chicago broke away from Antarctica's George VI ice shelf. The iceberg, designated A84 by satellite tracking systems, had been attached to the ice shelf for an unknown but certainly enormous length of time. When it finally calved and drifted away into the Bellingshausen Sea, it left behind something that no human eye had ever seen. A stretch of seafloor, completely untouched, completely unexplored. A patch of ocean bottom that had been sealed beneath thick ice for potentially centuries, and which, the moment A84 drifted away, was suddenly, astonishingly accessible. Scientists aboard the research vessel Falkor 2 were nearby. They had originally been conducting other research in the area, but the moment word reached them that A84 had calved, they redirected immediately. Using an underwater robot named Sebastian, they spent 8 days exploring the newly exposed seafloor, descending to depths of more than 4,000 feet. What they found was not a barren landscape, not a blank canvas. What they found was an ecosystem. A rich, complex, ancient ecosystem that looked as though it had been quietly flourishing for decades or possibly centuries, completely undisturbed in the cold dark beneath the ice. Giant vase-shaped sponges, organisms that grow so slowly, typically a fraction of a millimeter per year, that their sheer size implied ages of potentially hundreds of years. Sea anemones that resembled fluffy trees, their delicate tentacles extended into the current. Sea spiders, not true spiders, but marine arthropods that share spiders' body plan in a deeply unsettling way, some of them a foot across. Octopuses, icefish, brittle stars, crinoids, and creatures that the scientists weren't sure they recognized at all. Some of the organisms discovered during those 8 days of exploration appeared to represent species previously unknown to science. But then there were the jellyfish, the giant phantom jellyfish, officially known as Stygiomedusa gigantea, though that name feels almost too clinical for something so otherworldly, is one of the rarest marine organisms ever documented. It was first captured in 1899. By the time the 20th century had ended, it had been seen fewer than 115 times total anywhere in the world. The giant phantom jellyfish has a bell, the round, umbrella-like top portion of the animal that can exceed 3 feet in diameter. Its 4 ribbon-like arms, which it uses to capture prey and direct food toward its central mouth, can extend to 33 feet, the length of a school bus, trailing behind a translucent, purplish, ghostly body that seems to be made of something between flesh and water, something between solid and liquid, something that shouldn't quite exist in the physical world as we understand it. And here is the thing about the giant phantom jellyfish that genuinely unnerved the researchers who observed it beneath the ice. It moved deliberately. Jellyfish, as a rule, are not deliberate creatures. They drift, they pulse, they follow currents and respond to chemical gradients. Their nervous system, a diffuse network of cells spread throughout their body, rather than a centralized brain, gives them basic sensory capabilities, but is not generally considered capable of what we would call intentional behavior. But the phantom jellyfish, navigating the complex terrain of the Antarctic seafloor, was doing something different. It was threading its massive body through tight spaces in the rocky seafloor with what appeared to be careful, considered precision, moving its arms in coordinated patterns that seemed designed to avoid obstacles, behaving, in short, less like an organism drifting through the world and more like an organism navigating it. Scientists do not know what to make of this. The phantom jellyfish does not have a brain. It cannot think in any conventional sense of the word. And yet, it was doing something that looked, unmistakably, like thinking. Then, there were the icefish nurseries. In the Weddell Sea, in waters cold enough to shatter ordinary biology, researchers tracking whale populations from an icebreaker vessel noticed something strange on their camera feeds. The seafloor was covered in identical shallow bowls. Thousands of them. Then tens of thousands. Then hundreds of thousands. 60 million. That was the final count. 60 million nests, each about a foot in diameter, spread across 93 square miles of seafloor. Every 10 inches, another nest. Every nest containing approximately 1,700 eggs. Every egg guarded by a parent fish. The icefish, Neopagetopsis iona, a species that has evolved to survive in waters cold enough to kill almost anything else, are extraordinary on their own terms. They have no hemoglobin in their blood. Their blood is white. They have evolved over millions of years in the freezing Southern Ocean, a biology that runs without the oxygen-carrying pigment that virtually every other vertebrate on Earth depends on. Instead, they have enlarged hearts, wide blood vessels, and blood with unusual chemical properties that allow oxygen to dissolve directly into the plasma without the assistance of a carrier molecule. White-blooded, cold-adapted, building the largest known breeding colony of any fish species on Earth in waters that science had categorized as essentially too hostile for complex life. Antarctica keeps producing these moments, these encounters with organisms that don't play by the rules, and nothing reveals that more dramatically than what happens when a finger of death reaches down from the ice. Imagine you are a starfish. You have no brain, no centralized nervous system. A loose network of nerve cells distributed through your body gives you the capacity to sense light, detect chemicals in the water, feel vibrations in the seafloor. You move slowly, at most a few inches per minute, across a rocky Antarctic seafloor that has been your entire world since you were larvae. You are, by most measures, well adapted to your environment. The cold doesn't bother you. The pressure doesn't bother you. The darkness doesn't particularly bother you. And then, something descends from above. Not fast, not dramatically, not with any of the urgency you might expect from something deadly. It descends slowly, almost languorously, a column of ice forming in the water, growing downward from the frozen ceiling above, reaching toward you with the patience of geology. You have no concept of danger, no mechanism for processing what you are seeing. By the time the ice touches the seafloor around you, it is already too late. This is what scientists call a brinacle, and it is one of the most beautiful, most strange, and most lethal phenomena in all of Antarctic, or perhaps any. ocean. The formation of a brinacle begins with a fundamental property of seawater. When ocean water freezes, it doesn't freeze uniformly. Salt molecules are too large and too chemically disruptive to be incorporated neatly into the crystalline structure of ice. So as seawater freezes from the surface down, the ice that forms is fresh, essentially pure water, frozen into interlocking crystals. The salt gets left behind, concentrated into pockets and channels within the ice structure, creating a briny fluid that can be 3 to 8 times saltier than the surrounding ocean. This brine is heavy, dense, cold beyond normal seawater, sometimes dropping below 28 degrees Fahrenheit, colder than the point at which regular seawater would freeze, because the salt depresses the freezing point dramatically. And it's under pressure from the ice above, so it drains. It seeps down through channels in the sea ice, accumulating at the underside of the frozen ceiling, and eventually, when conditions are right, when the temperature differential between the brine and the surrounding seawater is large enough, when the current is calm enough, it begins to drip. And here is where physics becomes something close to alchemy. As the brine drips down into the surrounding seawater, it immediately begins freezing that seawater around itself. Not because the seawater is particularly cold, but because the brine is so cold, so dense, so chemically extreme that the water it contacts simply cannot remain liquid. The brine descends inside a self-generated sheath of ice, a tube of frozen seawater that grows downward, centimeter by centimeter, following the flow of the brine inside it. At first, the structure is fragile, a thin-walled tube of ice, almost transparent, hanging from the underside of the sea ice like an inverted icicle. The walls are a few millimeters thick. A passing current or a slight temperature fluctuation can snap it immediately. But if conditions hold, if the ocean stays calm, if the temperature differential remains, the tube thickens. The walls build up layer by layer as more seawater freezes around the descending brine. The structure becomes heavier, more robust, more stable, and it keeps growing. Scientists have documented brinicles reaching more than 6 feet in length, 6 feet of hollow ice hanging from the frozen ceiling of the ocean, slowly descending toward the seafloor, carrying within it a flow of liquid brine so cold that it freezes everything it touches. In 2011, a BBC Natural History film crew managed to capture a brinicle forming in real time, the first time this process had ever been filmed. The footage is extraordinary. You watch the ice structure descend, slowly, steadily, relentlessly, and then you watch it reach the seafloor. You watch the brine begin spreading outward across the rocky bottom, freezing as it goes, creating a thin sheet of ice that expands in all directions, and you watch the starfish trying to escape, failing, freezing in place, one by one, as the ice reaches them. The scientist who wrote about this footage described it as a slow-motion natural disaster. That's accurate. But it's also something else, something more philosophically interesting than a disaster. Because here is what researchers began realizing as they studied brinicles more carefully. These structures, these fingers of death, may be among the most chemically interesting environments on the planet. The brine channels in sea ice are not simply cold, salty water. They are concentrated chemical laboratories pockets of extreme chemistry where molecules can accumulate, react, and interact in ways that simply don't happen in the open ocean. And those chemical conditions might be relevant to something much bigger than the life and death of a single Antarctic starfish. Some researchers have begun examining brinicles not merely as natural phenomena, but as potential models for one of the most fundamental questions in science: how did life begin? The earliest life on Earth, whatever it was, wherever it originated, however it emerged from chemistry into biology, needed somewhere. It needed a place where raw chemical ingredients could be concentrated, where reactions could occur, where the building blocks of biological molecules could form, accumulate, and interact over and over again, across time spans that dwarf anything in human history. The brine channels in sea ice check many of those boxes. They are chemically concentrated. They are physically confined, providing the spatial constraints that promote molecular interactions. They experience the kind of cycling, freezing and thawing, concentrating and diluting that some researchers believe could have catalyzed the formation of the earliest biological molecules. In the brine channels of sea ice, scientists have found conditions that could theoretically produce amino acids, the building blocks of proteins. They've found conditions consistent with the formation of nucleotides, the building blocks of DNA and RNA. They found, in other words, conditions that might just produce life. And if those conditions exist here, in the sea ice of Antarctic waters, they might exist elsewhere. On Europa, on Ganymede, on Enceladus. The moons of Jupiter and Saturn are covered in ice. Beneath that ice, there are oceans, liquid water, kept liquid by tidal heating from their parent planets, sealed from space by a frozen ceiling that could be miles thick. And in that frozen ceiling, if the physics works the way we think it does, there could be brine channels. There could be brinicles. There could be chemical environments so similar to those in Antarctic sea ice that the same processes, the same chemistry, the same concentration, the same cycling could be occurring right now in the dark beneath alien ice, billions of miles from Earth. There's also one more remarkable chemical process happening in Antarctic waters, one that scientists named with what might be the best scientific nickname in history: bioduck. In 1960, researchers first recorded a strange, repeating sound in Antarctic waters, a low, quacking sound, repeated at consistent intervals, apparently emerging from the deep ocean. For decades, scientists puzzled over it. Was it a geological phenomenon, a mechanical artifact, some kind of biological signal from an organism they hadn't yet identified? The answer, when it came in the 21st century through improved acoustic analysis, was both mundane and magnificent. It was the call of minke whales. Specifically, the calls of minke whales that had apparently been developing and refining this particular vocalization for generations. A call so consistent, so rhythmically structured, that scientists initially assumed it had to be mechanical. But what made the bioduck discovery truly interesting wasn't just identifying the source. It was what the discovery revealed about cetacean communication. When researchers analyzed the patterns carefully, they found that the signals never overlapped. One whale would call, the others would fall silent. Then another would call, as if they were taking turns, as if they were engaged in a conversation, observing some form of acoustic etiquette that we had never previously attributed to baleen whales. And in 2023, researchers from the University of California took this a step further. They established what they described as a genuine conversation with a humpback whale named Twain off the coast of Alaska. Using a recording of Twain's own social calls broadcast through underwater speakers, they sent a greeting signal into the ocean and waited. Twain approached the boat, circled it, responded with a call of its own. The conversation, if that word applies, lasted 20 minutes and involved 36 exchanges, with the whale apparently observing a 10-second response window before replying, matching the interval the researchers had established. A whale, engaging in structured turn-taking communication with a research vessel, in waters that we used to call empty. Antarctica is not empty. It never was. There is a moment in the drilling process, a specific, quiet, almost ceremonial moment, when a core of ice comes up from thousands of feet below the surface and meets open air for the first time in over 1 million years. The scientists who experience this moment describe it differently. Some say it is humbling. Some say it is vertiginous, that strange feeling of looking down through time rather than through space. Some say that the ice core, as it emerges from the drill bore, makes a sound, a soft release of pressure, almost like a sigh. The air that was sealed inside that ice, the bubbles that froze in place as snow accumulated layer by layer, century by century, millennium by millennium, that air has been waiting, compressed and preserved in perfect darkness, at perfect cold, for a length of time that renders normal human temporal comprehension essentially useless. Until 2024, the oldest continuous ice core ever recovered extended back 800,000 years. That was extraordinary. That 800,000-year record had already transformed our understanding of the relationship between atmospheric carbon dioxide and global temperature, confirming in extraordinary detail that temperature and CO2 have risen and fallen in lockstep over hundreds of thousands of years of climate cycles, each cycle driven by subtle changes in Earth's orbit and amplified by the greenhouse effect. But then a team of researchers drilling at a site in East Antarctica, a location chosen after years of careful analysis of ice flow patterns, temperature gradients, and geological modeling, pulled up something older, a core dating to approximately 1.2 million years before the present. The oldest ice ever retrieved, ever touched by human hands. Inside that ice were bubbles, thousands of them, each bubble a tiny sealed capsule containing a sample of Earth's ancient atmosphere, the exact mix of nitrogen, oxygen, argon, carbon dioxide, methane, and trace gases that existed at the moment the bubble was sealed. Each bubble a direct physical sample of air that Homo erectus might have breathed, air that predates our species by a comfortable margin, air from a world so different from our own that attempting to truly imagine it produces a kind of cognitive vertigo. When scientists crack open these cores and analyze the gas inside, using instruments so sensitive they can detect individual molecules, they are not merely measuring ancient chemistry. They are taking the pulse of a planet. They are reading a record so detailed, so continuous, so precisely calibrated, that it can tell us not just what the atmosphere contained, but what the temperature was, what the sea levels were, how the ice sheets grew and retreated, how the ocean chemistry changed. And buried in that record, around 900,000 years ago, is something that should give everyone pause, a discontinuity, a change so dramatic, so abrupt in geological terms, that climate scientists have been arguing about its causes for decades. Before 900,000 years ago, Earth's major ice ages cycled on a roughly 41,000-year rhythm, tied to a wobble in Earth's axial tilt known as obliquity. After 900,000 years ago, the cycle shifted. Ice ages began occurring approximately every 100,000 years instead, linked to a different orbital parameter, the eccentricity of Earth's orbit around the Sun. Why did this shift happen? What drove the transition from 41,000-year cycles to 100,000-year cycles? Scientists have theories. Changes in the concentration of atmospheric CO2, changes in ocean circulation, changes in the bedrock geology beneath the ice sheets, but nothing definitive. The answer may be locked inside ice cores, even older than the one retrieved in 2024. Ice that may exist in Antarctica. Ice that may be recoverable. An archive so deep it extends back 3, 4, possibly 5 million years. But the climate transition is only the beginning of what that period, 900,000 years ago, means to us. Because around the same time, around 800,000 to 900,000 years before the present, something happened to our ancestors. Something catastrophic. Genetic studies published in 2023 analyzed the DNA of modern human populations and traced backward through the mutations, the genetic drift, the population dynamics, all the way to a bottleneck so severe it raises genuine questions about why humanity survived at all. Around 800 to 900,000 years ago, the ancestral population that would eventually give rise to all modern humans appears to have crashed, not declined, not contracted, crashed, from an estimated 100,000 or more individuals down to approximately 1,300. 1,300 people. That is the number. That is the slender thread from which every human being alive today descends. 1,300 people. That's smaller than most suburban high schools. That's smaller than the crowd at a middling local sports event. That's smaller, by a factor of several, than the population of researchers currently stationed in Antarctica at any given time. For roughly 100,000 years, a span of time so long it exceeds the entire period of anatomically modern human existence, our ancestors apparently lived on the edge of extinction. The reasons are not fully understood, but the timing is striking. The timing aligns with the Great Climate Transition. With the shift from 41,000-year Ice Age cycles to 100,000-year cycles, with a period of extreme climate volatility, massive glaciations, dramatic sea level changes, the reorganization of ecosystems across multiple continents. The ice cores from Antarctica can't tell us exactly what killed our ancestors. They can't speak with that specificity. But they can tell us what the planet was doing during that terrible century of near extinction. They can give us the atmospheric chemistry, the temperature swings, the glacial dynamics. They can tell us what the world that almost erased us looked like. And around the same time period, locked in the permafrost of Siberia rather than Antarctic ice, but preserved by the same principle of extreme cold. Scientists in 2021 found something almost as astonishing as the ice cores. They found a living organism, not a fossilized organism, not ancient genetic material they could analyze in a lab. A living, intact, viable, functional microscopic animal, a bdelloid rotifer that had been frozen in Siberian permafrost for 24,000 years. 24,000 years, not dead, not dormant in any superficial sense. Genuinely preserved at the level of every individual cell, every protein structure, every piece of genetic material, in a state of suspended animation so complete that when the permafrost around it thawed and the animal was exposed to liquid water, it woke up. It didn't just wake up, it reproduced. Through a process called parthenogenesis, in which an unfertilized egg develops into a new organism, essentially a clone of the mother. The rotifer began generating offspring within weeks of thawing. An animal that had been frozen since before the end of the last ice age, since before the woolly mammoth populations that roamed Siberia at the time had gone extinct, had simply resumed its biological existence as though nothing particularly unusual had happened. Scientists are studying the mechanisms that allow this. The chaperone proteins, specialized molecules that prevent other proteins from misfolding under extreme stress. The cryptobiosis that allows metabolism to essentially stop without causing cellular damage. The horizontal gene transfer, a process by which rotifers can incorporate genetic material from other organisms, bacteria, fungi, even plants, splicing foreign DNA into their own genomes and potentially gaining new survival tools. Up to 10% of an active rotifer's genome may consist of genes borrowed from completely different kingdoms of life. 10%. Borrowed. Because in Antarctica, in the permafrost, in the extreme environments that define the most hostile places on Earth, borrowing what works is better than reinventing everything from scratch. This is evolution at its most creative, and it is happening right now in the ice. Let's talk about volcanoes. Not abstract, theoretical, might be there someday volcanoes, real ones. 138 of them, confirmed by scientific survey, buried beneath the ice of West Antarctica, making it potentially the densest concentration of volcanoes anywhere on Earth's surface. 138. If you're struggling to hold that number in your head, try this. The entire Cascade Range of the American Pacific Northwest, one of the most volcanically active regions in the country, responsible for Mount St. Helens, Mount Rainier, and more than a dozen other major peaks, contains approximately 20 significant volcanic centers, spread across roughly 700 miles. West Antarctica contains 138 volcanic centers, buried under ice. Among them is Mount Erebus, the southernmost active volcano on Earth, standing more than 12,000 feet tall, continuously erupting for at least 1.3 million years. Erebus is extraordinary even among volcanoes. It maintains a permanent lava lake inside its summit crater, a pool of molten rock so persistent and so accessible that it has become one of the most intensively studied volcanic features anywhere on the planet. Scientists have measured its temperature, sampled its gases, analyzed its chemistry in extraordinary detail, And every single day, Erebus releases something remarkable: gold. Not in quantities that would make mining it remotely economical, not in nuggets or veins or any form that a prospector would recognize, but in microscopic particles, specks of gold smaller than the diameter of a human hair, carried upward in volcanic gases from deep within the Earth and dispersed into the Antarctic atmosphere. Erebus releases approximately 0.2 pounds of gold particles every single day. Over the course of a year, that adds up to more than 60 pounds of gold, worth approximately $2 million at current market prices, floating into the Antarctic sky. You cannot catch it. You cannot collect it. It disperses across hundreds of square miles. But it is there, every day, a reminder that beneath the frozen surface of Antarctica, the Earth's interior is very much alive and very much active. But the volcanoes beneath the West Antarctic ice sheet are more than geological curiosities, more than sources of scattered gold or dramatic geological features. They represent a feedback mechanism, a loop of cause and effect that could become one of the most serious drivers of climate change in the coming centuries. Here's how it works. The ice sheet exerts enormous pressure on the rock beneath it. Trillions of tons of ice pressing down on the volcanic systems below, acting as a kind of geological lid, keeping pressure high enough that magma stays contained, that gases don't escape easily, that volcanic activity remains relatively suppressed. But as the ice melts, as the Antarctic ice sheet loses mass, year by year, decade by decade, due to warming temperatures, that pressure decreases. And when pressure decreases over a volcanic system, things can happen. Magma that was previously too confined to reach the surface can find pathways upward. Gases that were dissolved in molten rock under high pressure can escape when the pressure drops. Volcanic activity that was held in check by the weight of miles of ice can intensify. This is not speculation. This is a documented phenomenon. After the last ice age, as the great ice sheets that once covered much of North America and Europe retreated, volcanic activity in previously glaciated regions increased dramatically. Scientists have found evidence of massive volcanic eruptions in Iceland and other glaciated areas during the period of rapid ice retreat. Eruptions that appear to have been triggered, or at least enabled, by the removal of glacial pressure. What might happen in Antarctica is potentially of a different order entirely. If the ice sheet retreats significantly, and the most pessimistic models of climate change suggest that West Antarctica's marine ice sheet could be subject to irreversible, potentially rapid collapse, the reduction in pressure could trigger increased volcanic activity across those 138 volcanic centers, and increased volcanic activity could accelerate ice loss. Not primarily through heat. The direct melting effect of a subglacial volcano on the ice above it is relatively modest. But through geothermal heating of the bedrock, through the introduction of heat into the subglacial meltwater network, through the physical disruption of ice sheet dynamics in ways that scientists are still working to model. Ice melts. Volcanic activity increases. Volcanic activity generates heat and introduces additional liquid water beneath the ice. That water lubricates the ice sheet's base, allowing it to flow faster toward the ocean. More ice reaches the ocean. More ice melts. Pressure decreases further. The loop feeds itself. This is what climate scientists call a positive feedback, a mechanism that amplifies its own cause. And what makes it particularly concerning is the time scales involved. A positive feedback loop in a system as massive and as complex as the Antarctic ice sheet doesn't respond instantly. It can take centuries to develop. It can take centuries to reverse. And once it reaches a certain threshold, once the loop is spinning fast enough, it may not be possible to stop it at all, even if humanity reduced its carbon emissions to zero tomorrow. The Thwaites Glacier, already nicknamed the Doomsday Glacier by scientists and science communicators alike, though not without reason, sits in West Antarctica, draining a portion of the ice sheet roughly the size of Florida. It is currently losing ice at an accelerating rate, with its grounding line, the point where the glacier lifts off the seafloor and begins floating, retreating faster than any comparable glacier in Antarctica. If Thwaites collapses, if its ice shelf disintegrates and allows the glacier behind it to flow freely into the ocean, the contribution to global sea level rise could be 3 feet or more. That alone would be catastrophic for coastal communities worldwide. But Thwaites isn't isolated. It is a plug in a bathtub. And behind it, held back by its presence, is significantly more ice. Enough, if it all eventually made its way to the ocean, to raise global sea levels by 10 feet or more. Antarctica holds 70% of all the freshwater on Earth. Locked in ice. Locked in the geological freezer that has kept this continent cold for 34 million years. If that freezer begins to fail, if the loop begins to spin, the consequences will not be limited to Antarctica. They will not be limited to any coastline, any city, any country. The consequences will reshape the geography of human civilization. This is why the autonomous submarine Ran, built and operated by the University of Gothenburg, was deployed to map the underside of Thwaites. This is why it spent 27 consecutive days beneath the ice in 2019, traveling more than 600 miles through absolute darkness, mapping the topography of the glacier's underbelly in unprecedented detail. This is why, when Ran disappeared beneath Thwaites in early 2024, heading into the glacier's belly and simply not coming back, no distress signal, no final transmission, no wreckage found despite extensive aerial and drone searches, the scientific community mourned not just the loss of an extraordinary piece of technology, but the loss of a window into a place that may be among the most consequential on Earth. Ran found things in its earlier missions that startled even experienced glaciologists. The underside of Thwaites was not smooth. It was scarred with ridges and troughs, pockmarked by massive melt cavities where warm Atlantic water had worked its way beneath the ice and eaten it from below. It found swirling, teardrop-shaped formations, hundreds of feet long, carved by rotating ocean currents, amplified by the Coriolis effect of the Earth's rotation. It found evidence that the melting was not uniform, not predictable, not following the simple models that had been used to project Thwaites' future. The glacier was more complex. The melting was faster in some places, slower in others, driven by ocean circulation patterns that shifted seasonally and interannually in ways that made precise prediction enormously difficult. What Ran found in 2024, before it disappeared, we do not know. Its data, whatever it collected in those final hours of operation, may still be encoded in its memory, sealed inside whatever remains of the submarine, lying somewhere beneath Thwaites in the dark. Some of the most important information about the future of human civilization may currently be sitting at the bottom of a glacier, in the dark, in a piece of technology we cannot reach. Antarctica keeps its secrets, but some of those secrets are not abstractions. Some of them are urgently, immediately, practically important, and some of them are written in bone. In 1985, a Chilean biologist named Dr. Daniel Torres was doing what Antarctic researchers do routinely: cataloging, counting, recording. He was conducting a census of mammals and collecting marine refuse on Cape Shiref in the South Shetland Islands, just off the northern tip of the Antarctic Peninsula. He reached down to pick up what he thought was a piece of plastic debris. It was a skull. A human skull, female, young, probably in her early 20s, and from the morphological characteristics, the shape of the cheekbones, the brow ridge, the dental structure, almost certainly of Chilean origin. Indigenous to southern Chile, most likely. Dr. Torres had been in Antarctica many times. He had never expected to find a human skull. The discovery launched years of investigation. Several years later, additional bone fragments, sections of femur, were found at the same site and subjected to DNA analysis. The results confirmed what the morphological evidence had suggested. The bones belonged to the same individual, one young woman, in her early 20s, malnourished at the time of her death. How did she get there? Cape Shiref was a known camping location for sealers operating in the South Shetland Islands in the early 19th century. The sealing industry was brutal, relentless, and enormously profitable, at least until the seal populations collapsed from overhunting, which they did with tragic speed. Ships from Britain, America, and the America's own coastal nations worked these waters in the early 1800s. But women did not go on sealing voyages, not in 1820, not in 1825, not ever, as a general rule, in those decades when the sealing industry was most active in the region. The ships were crowded, dangerous, and entirely male-crewed operations. The presence of a young indigenous Chilean woman on such an expedition would have been extraordinary, unprecedented, and almost certainly documented. And yet there were no documents, no ship manifests, no journals, no records of any kind that could explain why a young woman from southern Chile had died at Cape Shiref sometime in the early 19th century, during the period when Antarctica was first being actively explored and exploited. There was nothing else at the site, no tools, no personal effects. No objects that could tell investigators who she was, how she arrived, what she was doing there, or what killed her. One interpretation, one that some researchers have found intriguing enough to pursue, is that she was not a passive passenger or an accidental presence. That she, or the people with her, had established a presence at Cape Shiref before the European and American sealers arrived. That she represents evidence of a history of southern Chilean maritime activity in the islands that predates the documented discovery of Antarctica. We may never know, but the skull sits in a Chilean museum now, and the mystery it represents has not been solved. It is not the only human ghost haunting Antarctica's past. On May 19, 1845, Two ships departed from Greenhithe, England. The HMS Erebus and the HMS Terror, both vessels reinforced against Arctic ice, equipped with steam engines to supplement their sails, provisioned for 3 years. Their commander was Sir John Franklin, a veteran Arctic explorer with 4 decades of naval experience. Their mission was to find and navigate the Northwest Passage, the sea route through the Canadian Arctic that, if successfully navigated, would provide a dramatically shorter path between the Atlantic and Pacific Oceans. It was to be the defining expedition of the age. 134 men sailed north on those 2 ships. No one heard from them again. Search parties began in 1847. Dozens of expeditions over the following decades probed the Canadian Arctic for survivors, for wreckage, for any clue at all. Inuit oral histories provided fragmentary accounts of sick, starving men dragging sleds across the ice. Written messages found in cairns told part of the story. The ships had become trapped in ice in September 1846 and remained locked until April 1848. Franklin himself had died in June 1847. The survivors, by then reduced to 105 men, had abandoned the ships and attempted to walk to safety. None of them made it. In 2014, Canadian scientists announced the discovery of the wreck of HMS Erebus, lying on the seafloor of Nunavut's Queen Maud Gulf. 2 years later, HMS Terror was found approximately 45 miles away. Both ships were in extraordinary condition, preserved by the freezing cold of their watery graves. When underwater archaeologists entered the cabins of the ships in subsequent years, they found something that stopped everyone cold. Everything was still in place. Dinner plates arranged on shelves, glasses unbroken, beds made or unmade as they had been left. Personal belongings, clothing, boots, navigational instruments, personal effects, distributed throughout the ships as though their owners had simply stepped away temporarily and intended to return. The deep cold had preserved these ships so perfectly, for so long, that they stood as monuments to the final hours of 134 men. A moment of catastrophe. Frozen in time. Preserved in darkness. Waiting nearly 170 years for us to find them. But the most extraordinary survival story in the history of Antarctic and Arctic exploration isn't the story of the Franklin expedition. It's the story of the man who set out to cross Antarctica and ended up doing something far more remarkable. Ernest Shackleton. In August 1914, the ship Endurance sailed from England toward the Weddell Sea. Shackleton's plan was audacious, a complete overland crossing of Antarctica, from the Weddell Sea to the Ross Sea, a journey of 1,700 miles through the most hostile terrain on Earth, passing through the South Pole. It never happened. On January 19, 1915, the Endurance became trapped in pack ice in the Weddell Sea. The ice wasn't just thick around the ship, it was moving. Driven by ocean currents and wind, the ice pack was carrying the ship northward while simultaneously crushing it. For months, the crew camped on the ship, maintaining it as best they could, hoping the ice would eventually loosen. It didn't. On November 21, 1915, the Endurance sank. Crushed by the ice over a period of weeks, she went down quickly at the end, the bow lifting, the stern plunging, disappearing beneath the ice into 3,000 feet of ocean. 28 men were now stranded on the Antarctic ice pack with 3 small lifeboats, limited supplies, and no means of communication with the outside world. What happened next is perhaps the most remarkable survival story in human history. Over the following weeks and months, the crew of the Endurance endured conditions that would have broken most people. They camped on drifting ice floes. They traveled in their lifeboats across the Drake Passage, the stormiest ocean on Earth, in vessels designed for coastal use, not open ocean survival. When they finally reached land, the uninhabited Elephant Island, it was the first solid ground they had stood on in almost 500 days. And then Shackleton took 5 men and the smallest of the lifeboats and attempted to sail 800 miles through the open Southern Ocean to South Georgia Island, where a whaling station offered the only realistic hope of rescue. The journey took 16 days, in conditions so brutal that experienced sailors who heard the account afterward said it couldn't have been done. It was done. Shackleton reached South Georgia on May 20th, 1916. After a 36-hour crossing of the island's uncharted mountains and glaciers, he reached the whaling station at Stromness and began organizing the rescue of the 22 men still stranded at Elephant Island. On August 30th, 1916, the rescue vessel approached Elephant Island through drifting ice. Shackleton counted the figures on the shore. 22 men, all alive, every single one. In 2022, a search expedition using state-of-the-art sonar technology and underwater drones located the wreck of the Endurance on the seafloor of the Weddell Sea, at a depth of approximately 10,000 feet, in water so cold and dark and still that the ship had been preserved with almost impossible perfection. The name on the stern, still readable. The timbers, encrusted with sea life but structurally intact. In 2024, a complete 3-dimensional scan of the wreck was made using underwater robots. Thousands of photographs stitched together into a digital model so detailed you can read the grain of the wood. A ship that sank in 1915, perfectly preserved, in the dark, waiting, like everything else in Antarctica, to be found. Here is a thought experiment. Imagine you are a scientist at NASA. You have spent your career searching for signs of life beyond Earth. You have studied the Mars data, the Cassini data from Saturn's moon Enceladus, the Hubble spectroscopy of distant exoplanets. You know, better than almost anyone alive, the conditions that life might require. And one day, someone tells you that on your own planet, not on Mars, not on Europa, but right here on Earth, there is a place where those exact conditions exist. A place with a liquid ocean beneath a frozen surface. A place with chemistry driven by ice-water interactions rather than sunlight. A place where life has found ways to survive in total darkness, in extreme cold, in isolation so complete that evolution has had to get creative. Antarctica. It is not an exaggeration to say that Antarctica has become the most important training ground for astrobiology, the science of life in the universe, available to us. Every discovery made in its subglacial lakes, every organism found beneath its ice, every chemical process documented in its sea ice provides a data point for understanding where life might exist beyond Earth. Let's start with Europa. Europa is Jupiter's 4th largest moon, a world roughly the size of Earth's own moon, with a surface of cracked brownish ice that suggests a dynamic, active geology beneath. Scientists believe that beneath Europa's icy surface, which may be 5 to 15 miles thick, there is a liquid water ocean. Not a small one. Potentially an ocean containing twice as much liquid water as all of Earth's oceans combined. That ocean has likely been liquid for billions of years. It is kept liquid not by solar heating. Europa is far too distant from the sun for that, but by tidal heating, the gravitational squeezing of Europa's interior by Jupiter's enormous gravitational field, which generates heat through friction. And in that ocean, in that dark, warm water sealed beneath miles of ice, the same basic chemistry that operates in Antarctic subglacial environments would presumably apply. Ice-water interfaces, mineral-rich water flowing through rocky seafloor, chemical energy sources that life could potentially exploit. NASA's Europa Clipper mission, launched in late 2024, is designed to make detailed measurements of Europa's ice shell, its ocean, its surface chemistry, and its magnetic field. The data it returns over the next decade will dramatically refine our understanding of whether Europa's ocean is hospitable to life. But the frameworks we use to interpret that data, the baseline understanding of how life can exist in ice-covered, chemically extreme, dark environments, that baseline is being built in Antarctica right now. Then there's Enceladus. Saturn's sixth largest moon is, in some ways, even more exciting than Europa. Enceladus is small, only about 300 miles in diameter, but it is erupting. Geysers of water vapor and ice particles shoot from cracks in its southern polar region, launching material into space at velocities high enough to escape Enceladus's gravity and create Saturn's E-ring. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through these geysers multiple times. The data it collected was staggering. The erupting material contained water, carbon dioxide, methane, ammonia, molecular hydrogen, and, crucially, complex organic molecules, including silica nanoparticles that could only have formed in water at temperatures above 175 degrees Fahrenheit, implying hydrothermal activity on Enceladus's seafloor. Hydrothermal activity in a liquid ocean, beneath ice, on a moon of Saturn. If Antarctica has taught us anything, it is that life doesn't need sunlight. It doesn't need warmth at the surface. It doesn't need familiar chemistry. Life needs energy, some source of chemical or thermal energy, and liquid water. And wherever those two things coexist for long enough, in enough volume, life on Earth finds a way. The McMurdo Dry Valleys, a stretch of ice-free terrain in Victoria Land, have been used as a training and testing ground for Mars exploration technology for decades. The valleys are bone dry. They are swept by katabatic winds of extraordinary violence. They receive almost no precipitation. And yet life exists there, in forms so extreme they constitute their own catalog of evolutionary marvels. Endolithic bacteria, organisms that live inside the rocks themselves, inhabiting the tiny airspaces between mineral grains, subsisting on the trace amounts of light that filter through translucent stone, performing photosynthesis in slow motion in amounts so small that a single gram of rock might contain the total photosynthetic output that a leaf produces in a second. At Blood Falls, a rust-red waterfall that pours from the Taylor Glacier into Lake Bonny, staining the ice and snow with iron-rich brine. Scientists have discovered bacteria that have been completely isolated from the surface world for an estimated 2 million years. These organisms don't use oxygen. They don't use sunlight. They derive their energy from sulfur and iron chemistry, a metabolic strategy called chemolithotrophy, breaking the chemical bonds of iron sulfate minerals and extracting the electrons released by that process to power their cellular machinery. 2 million years in total darkness, in water so salty and so cold it barely qualifies as liquid by normal standards. Using chemistry. And then there is the Mars connection, more direct and more physical than any metaphor. In 2000, a Japanese research team working in Antarctica recovered a meteorite. Analysis of the gas trapped in its tiny pores, the ratios of oxygen isotopes in its minerals, and the specific pattern of its crystal structure pointed to a single, extraordinary conclusion. This rock had come from Mars. Approximately 15 million years ago, an asteroid struck the Martian surface with enough force to blast material from the Martian crust into space. Those pieces traveled through interplanetary space for millions of years before eventually intersecting with Earth's orbit. This particular piece, a 28-pound chunk of another planet, fell through Earth's atmosphere, survived the entry, and landed on the Antarctic ice, where it was preserved for millions of years. In 2025, this meteorite, one of the largest Mars meteorites ever recovered, was placed on display at the World Expo in Osaka, Japan. Inside this piece of Mars, scientists found special minerals that form only in the presence of liquid water. Evidence that sometime in Mars's distant past, when the planet was warmer, wetter, more similar to Earth, water had flowed through this rock. Water on Mars. In rock now sitting in Antarctica. The connections between these places, between Antarctic science and extraterrestrial exploration, between the extreme environments of Earth's last great wilderness and the alien oceans of other worlds, are not metaphorical. They are direct, practical, scientific connections that are currently shaping how we look for life beyond Earth. Antarctica is where we practice. Antarctica is where we learn. Antarctica is where we ask the questions that we will eventually carry to other worlds. And it keeps giving us new questions to ask. In 2017, scientists drilling beneath the Ross Ice Shelf, looking for water, finding the expected, suddenly had their cameras swarmed. Hundreds of tiny, shrimp-like creatures, amphipods, rushing toward the light of the underwater camera in waters nearly 1,600 feet below the surface of the ice. DNA traces in the sediment indicated the presence of moss, algae, and possibly organisms that hadn't been formally classified yet. In 2021, while drilling through the Larsen Ice Shelf in December, a team drilling a monitoring hole discovered that their Antarctic underground river contained fast-moving amphipods in such numbers that the animals were clogging the survey equipment. And on December 20th of that same year, the team noticed something in their pressure readings. A volcano had erupted that day in Tonga, in the Pacific Ocean, thousands of miles away. The pressure waves from that eruption traveled through the water and ice of the entire Southern Ocean and were detected in the underground river beneath the Larsen ice shelf in Antarctica, an eruption in the Pacific, felt in an underground river in Antarctica. Everything on this planet is connected. Everything. And Antarctica is the place where those connections are most clearly, most dramatically, most unmistakably revealed. Let's come back to where we started. An Italian research team. A lake that shouldn't exist. 36 feet of permanent ice. Liquid water. Life. Everything we have explored together. The self-replenishing mystery of Enigma Lake. The alien microbial communities beneath the ice. The deadly beauty of brinicles. The million-year-old bubbles of ancient air. The hidden volcanoes. The ghost ships. The organisms that eat iron in the dark. The connection to Europa and Enceladus and Mars. All of it originates from the same fundamental truth. Antarctica is not a wasteland. It is a record, the most complete archive of Earth's history that exists anywhere on the planet. Layer by layer, in its ice, you can read the story of our climate going back at least 1.2 million years, and potentially much, much further. In its subglacial lakes and rivers, you can find biological communities that have been evolving in isolation for periods of time that dwarf the entire history of human civilization. In its seafloor, beneath where great icebergs once sat, you can find ecosystems of extraordinary richness and age, preserved by darkness and cold in ways that nothing else on Earth can manage. And it is under threat. Not literally burning. Not yet. But the ice is leaving. The glaciers are retreating. The sea ice is thinning and shrinking. The Thwaites Glacier is losing mass at a rate that scientists describe, without exaggeration, as alarming. The feedback loops, volcanic, hydrological, thermal, are complex and not fully understood, but the trajectory is not ambiguous. The library is warming. And in a warming library, the books begin to disappear. The ice cores that hold the ancient atmosphere, those irreplaceable million-year-old records of Earth's climate, are stable only as long as the ice around them remains intact. The subglacial lake ecosystems that have been evolving in isolation for hundreds of thousands of years are vulnerable to the introduction of new organisms, new chemistry, new conditions. The frozen records, the wooden ships, the ancient tools, the biological specimens, the geological archives are only preserved as long as the cold is maintained. There is an urgency here that goes beyond any particular species or ecosystem, beyond any particular scientific question or research program. We are in a race with time. Not the human-scale time of political cycles or scientific careers, but geological time. The kind of time in which ice sheets grow and retreat, in which species evolve and go extinct, in which continents drift and mountain ranges rise and fall. Antarctica does not need us to survive. It has been surviving for 34 million years without us. Or rather, in the absence of anything resembling modern human civilization. It can go on surviving in whatever transformed state climate change delivers it to, for millions of years more. But we need it. We need the records it holds. We need the science it enables. We need the window it provides onto our planet's past. A past that is increasingly relevant to our future. We need the organisms it harbors, the chemistry it demonstrates. the evolutionary solutions to extreme environments that it has been quietly developing since before our ancestors descended from the trees. We need the library. In 1959, 12 nations signed the Antarctic Treaty, an agreement to preserve Antarctica for peaceful scientific purposes, to ban military activity, nuclear testing, and weapons testing, and to protect the environment. 54 nations are now party to this treaty. It is, in many ways, one of the most remarkable international agreements in human history, a commitment made and renewed over more than 60 years to treat an entire continent as a shared scientific and environmental heritage. That commitment needs to extend further, deeper, into the policies that govern climate change, that determine how much carbon we pump into the atmosphere, that shape the rate at which the ice will melt and the records will be lost, because every fraction of a degree of warming, every metric ton of carbon dioxide that we choose to emit or choose to spare has consequences for Antarctica, for the ice, for the records, for the life that has evolved there in the dark. The organisms in Enigma Lake have been waiting in darkness for hundreds of thousands of years. The brinicles have been forming and melting and reforming through ice ages and interglacials. The frozen ships have lain in the cold dark of polar seas for more than a century, perfectly preserved, waiting for the technology that would allow us to find them and understand what happened. Antarctica is patient. It has always been patient. It operates on timescales that make human history look like a rounding error, but it is not infinitely patient. The ice remembers everything, and we are running out of time to listen. If you have made it to the end of this journey, through the impossible lake and the alien organisms and the fingers of death and the ancient air and the hidden volcanoes and the lost ships and the search for life beyond Earth, then you already know something that most people don't. Antarctica is not empty. It is full. Full of secrets, full of life, full of history, full of answers to questions we haven't even learned to ask yet. The continent keeps surprising us, keeps rewriting what we thought we knew, keeps revealing, at the very edge of the possible, that the world is stranger and richer and more complex than any map we've drawn of it. And somewhere beneath its ice, in the dark, in the cold, in the silence, something is still alive that has never seen the sun. Something that has been down there since before humans walked the earth. Something that, if we are careful enough, and curious enough, and wise enough, might teach us more about life than we have ever imagined possible. Antarctica is not what we thought. It never was. And we are only just beginning to understand what it truly is. Thank you for being here. Sleep well, and dream of the ice.